combination reaction is the combination of two or more simple substances to form one complex substance. So we have here a general equation. Simple substances A and B combine to form one complex substance AB. Okay? Examples. So I have here common examples of combination reactions. Let's start with number 1. When you combine metal and non-metal, you form metal oxide. So one good example is the combination of metallic calcium and oxygen gas. So as the two combine, we form metal oxide, calcium oxide. Again, why is it that calcium has no subscript or any other number? Because this is simply an element. Oxygen has subscript too because again, when you encounter any of the 7 diatomic molecules in equations, you make use of subscript 2. That means that they are existing in nature as diatomic molecules. The product CaO, notice the absence already of subscript 2 in oxygen. Because calcium and oxygen is a combination of positive and negative ions. So, as I emphasized in last videos, in other videos, whenever combining positive and negative ions to form a compound, you always apply or use the crisscross method. The fixed charge of calcium is positive 2, the fixed charge of oxygen is negative 2. You crisscross the numeric, only the numeric charges, you disregard the charges, and then since they are 2 and 2, you simplify them to 1 and 1. So that's the reason why calcium and oxygen in the product side here have no subscripts already, because they are already simplified from 2 is to 2 to 1 is to 1. And then putting coefficients 2 is making the equation balanced. So whenever you write a chemical equation, you always see to it that it is balanced. Number 2, non-metal and oxygen to form non-metal oxide. So if you have number 1, metal plus oxygen to form metal oxide, you also have non-metal and oxygen to form non-metal oxide. One simple example is the combination of sulfur and oxygen gas. So that will form sulfur dioxide. Unlike number 1, that is ionic, number 2 is covalent. So in covalent bonding, we consider the sharing of electrons for the atoms to obtain their octets or the required number of valence electrons for their stability. So in the case of number 2, the equation is already balanced without putting any coefficients. So there are reactions that are already balanced even without adding any coefficients, such as this example. Number 3, metal and non-metal to form salt or binary salt. So this will be a combination of a metal and non-metal to form a binary ionic compound. So in this example, we have potassium and fluorine. So as they combine, they will involve exchange, transfer of ions. As I have mentioned in the last video, metals have the general tendency to give up or lose electrons during chemical reactions or chemical bonding. On the other hand, non-metals have the general tendency to gain electrons. So when a metal and non-metal combine, metal will give up and non-metal will accept the electron. So there is a transfer of electrons. In writing their chemical formula, you again apply the crisscross method because it is a combination of positive and negative ions. So putting coefficient 2 in front of potassium and 2 in the formula or in front of the formula of the product potassium fluoride will again balance the equation. To read the reaction again, 2 moles of metallic potassium combines with 1 mole of fluorine gas to form 2 moles of potassium fluoride. Another example is metal oxide plus water. So what forms when metal oxide further combines with metal with water? The two will form a base or a metal hydroxide. So one good example is here. So we have the metal oxide, sodium oxide plus water to form sodium hydroxide or metal hydroxide. So notice Na sub 2O for sodium oxide it's ionic. So you again apply the crisscross method. You consider the numeric charges of sodium and oxygen. So we have positive 1 of sodium and negative 2 of oxygen. So that's crisscrossing the numeric charges. That's why sodium has subscript 2, oxygen no subscript. Okay? Water is H2O and liquid, automatically liquid at room temperature to form sodium hydroxide. So again, sodium hydroxide is a combination of positive, negative, and whenever you are writing chemical formulas, you always consider the positive, negative combination and always apply or use the crisscross method. Next, and the last one, number 5. Non-metal oxide is further combined with water to form an acid. So if number 4 forms a base, number 5 forms an acid. Let's now go to decomposition. One complex substance breaks down to 2 or more simple substances in decomposition reaction. So we have here the general equation. So complex substance AB decomposes to simple substances A and B. Let's have some examples. So we have here a metallic oxide decomposing to its components, metal and oxygen. So one good example is the decomposition of silver oxide. Silver oxide is heated as indicated by the triangle over the arrow to produce or to break down to its components silver and oxygen. So adding coefficient 2 in front of silver oxide and 4 in front of the formula of silver or symbol of silver, balance the equation. Okay, so that's breakdown of metal oxide to components, metal and oxygen. Let's have example number 2. Metal chlorate decomposing to or breaking down to metal chloride and oxygen. Why is it called metal chlorate? Metal chlorate is called metal chlorate because of components metal and chlorate. So metal and chlorate are 2 ions. So in writing the formulas again and again, you use the crisscross method. So when a metal chloride breaks down or decomposes, they form 2 products, metal chloride and oxygen. So adding coefficients 2, 2, and 3 respectively will balance the equation. Let's have the third example, metal carbonate. When metal carbonate decomposes, it forms metal oxide and carbon dioxide. So calcium carbonate, when heated, breaks down to calcium oxide and carbon dioxide. When metal hydroxide, example number 4, decomposes, metal oxide and water form. So one example is magnesium hydroxide. So again, hydroxide is a polyatomic anion. Magnesium has numeric charge of positive 2. So numeric charge of 2 is brought down, crisscross to the polyatomic ion OH that makes it enclosed in parentheses with subscript 2. When that compound, metal hydroxide, magnesium hydroxide, decomposes, it forms or it breaks down to, it forms 2 substances, magnesium oxide and water. And then balancing the equation, you don't need any coefficient here because 1, 1, 1 coefficients already make the equation balance. For miscellaneous reactions, we have silver chloride is a binary salt. So when binary salts like silver chloride decompose, they form or break down to their components. Such in this case, silver chloride is broken down to its components, silver and chlorine gas. Another is the hydrolysis of or electrolysis of hydrogen peroxide to form water and oxygen gas. And the third one, we have sodium nitrate decomposing to sodium nitrite and oxygen gas. So again, the coefficients are to balance the chemical equations. Next, go to the third chemical reaction. We have single replacement. Single replacement involves replacement of a free element of another element in a compound. We can consider two general equations here. We have equation 1A replacing B from substance BC to form AC plus or and the replaced element. Or the other equation, substance A or free element A replacing element C from BC compound to form a compound BA and the element replaced. What makes them different? It has something to do with the nature of the free element replacing another element. In analyzing singular replacement reactions, we consider the activity series. Activity series of metals can be seen on this illustration. So you will see here common metals, common reactive metals ranging from potassium down to mercury. Notice the trend from the bottom to the top, it's increasing. So that means the one on top is the most active metal and the one at the bottom is considered the least active. What does it mean for the activity series of metals? When a free element is of a higher position than the element it will replace from a compound, it means that the single replacement reaction is possible. For example, potassium can replace all those elements below it from a compound in a single replacement reaction. On the other hand, mercury, being the least active, cannot replace any of the elements above it because they are more active than it. Okay? So again, let's have two examples. Let's combine magnesium and zinc. Magnesium is higher in the position, therefore more active, therefore capable of replacing zinc in a compound. So that's how we use the activity theory series of metals when analyzing or predicting products in single replacement reactions. Let's have then some examples. So we have here aluminum as the free element combining with copper sulfate. Notice the free element is a metal. So if it's a metal, what it will replace from the compound is also a metal. So metal replaces metal in a single replacement reaction. So what is the metal in copper sulfate compound? It is copper. And then looking back at the activity series, let's compare the positions of aluminum and copper. Is aluminum capable of replacing copper from the compound copper sulfate? Let's take a look. We have the position of aluminum that is higher or lower than that of copper. It is higher. So aluminum is much more reactive than copper. So aluminum can replace copper in copper sulfate. So when aluminum replaces copper from copper sulfate, the products will be aluminum sulfate. And the other product is that element that is replaced by aluminum. So the pattern here, A is metal, BC compound is composed of copper, which is the metal, and sulfate, which is the non-metal. So metal aluminum replaces B, metal aluminum, metal copper. The products will be AC pattern. AC pattern. The other substance from the general equation B is replaced as another product. So that's when we use the first general equation in the previous slide. And then adding coefficients 2, 3, 1, and 3 respectively will balance the equation. Although we have some exceptions. Notice in the activity series, we have one element that is non-metal. It is the activity series of metals, but we observe one non-metal, which is hydrogen. And where is the position of hydrogen? It's below, it's next to lead. It's before copper. So what does it mean? hydrogen can be replaced from a compound by any metal above it in the activity series, but cannot be replaced by those metals below it from a compound. Okay? For example, magnesium combines or reacts with hydrogen chloride in the reaction. Let's take a look at the positions of magnesium and hydrogen in the activity series. Is magnesium capable of replacing hydrogen? Let's see. Yes. Magnesium is higher in the activity series than hydrogen. Therefore, it can replace hydrogen from a compound. So when it replaces when magnesium replaces hydrogen from the compound hydrogen chloride, the products will be hydrogen is the element replaced by magnesium, and then the new product will be magnesium chloride, the pattern AC. When considering the general equation. Another exception is, and then putting 2 to balance equation, another exception is when that non-metal is less active than the element it will replace. For example, silver is a metal, copper is the metal in copper chloride. So copper is more active than silver, or silver is less active than copper, so it cannot replace copper from copper chloride, and therefore no reaction or single replacement reaction is possible in this case. Let's have another example. When the free element this time is non-metal, it will need to replace non-metal as well. So in this example, chlorine is non-metal. Calcium bromide contains the non-metal bromine. So when these two combine, then the free element non-metal chlorine will have to replace the non-metal bromine from the compound calcium bromide. So replacing bromine in carbon bromide will result to formation of the products calcium chloride and bromine. So bromine is the element replaced by chlorine in the reaction. So if we have activity series for metals, we also have activity series for non-metals. So as you can see here, among the most active non-metals or halogens, we have fluorine as the most active in the topmost position, while iodine in the lowest position or the bottom means that it is least active of all the halogens. Let's go to the last type. We have double displacement. Double displacement is sometimes called ionic exchange reaction because it involves exchange of positive and negative ions. So the general equation for all double replacement reaction is compound AB combines with compound CD to produce substances AD plus CB. So we have here pairs of ions. Positive A and negative B pair plus positive C and negative D pair to form another 2 pairs, positive A and negative D compound or pair, and positive C and negative B compound. So you will see here exchange of partners. Let's have some examples. Example number 1, acid-base neutralization. When an acid reacts with the base, they form 2 products, salt and water. So if we are to use the general equation, what are our A, B, C, D, A, D, C, B compounds? So we have here hydrogen chloride as the acid combines with sodium hydroxide, which is the base, to form sodium chloride, which is the salt, and water. So which is our positive ion A? That is hydrogen. Hydrogen positive 1 is the numeric charge. Our negative ion B is chloride. Chloride is negative 1. Our CD pair of ion is sodium, positive 1 as our C. OH, negative 1 is our ion D. So they will simply exchange partners. So from the general equation, one of our 2 products pattern is AD. So what is again our AD pairs of ions from the from the reactants here, we have AH and OH D. So combining H and OH, we will form water. So water is one of the two products in an acid-base reaction or neutralization. What about the sodium chloride? That is our pattern CB. Our C ion is Na positive 1, sodium positive 1. Our B ion is chlorine negative 1 or chloride. So combining C and B, we will form NaCl. And then coefficients 1, 1, 1, 1 respectively balance the equation. Another example number 2, formation of an insoluble precipitate. So we have here aqueous. Silver nitrate combines with sodium chloride to form silver chloride and sodium nitrate. So we again make use of the general equation ABCD, forming AD and CB. So you have positive negative plus positive negative to form positive negative and positive negative. So you're just exchanging the ions, but still considering the crisscross method when predicting, for example, the products. Another is the combination of a metal oxide and an acid. So we have here, to form salt and water. So we have here a metal oxide, copper oxide, combining with nitric acid to form a salt, copper nitrate, and water. So you will notice here the, again, positive negative, copper positive, oxide negative, nitric acid, hydrogen positive, nitrate negative. So we have A, B, C, D to form AD, copper nitrate, and CB, water. And then adding coefficient 2 in front of the formula of our acid will balance the equation. Another one is the formation of a gas. So we have here an example, sulfuric acid plus or combines with sodium cyanide to form sodium sulfate and hydrogen cyanide or cyanic acid. So we have AB, again AB, hydrogen, A or positive 1 ion, sulfate negative 2, our B. C is Na positive 1, Cn is negative 1. So we have AB, CD. So what is our AD pattern? AD pattern is H and Cn. AD. So we will have hydrogen cyanide. Our CB pattern is Na and SO4 for sodium sulfate. And adding again coefficients 2 in sodium cyanide and hydrogen cyanide make our equation balance. So those wrap up the types of chemical reaction. Let's try to answer this. So to do this, you will write the balanced chemical equation and classify the reaction as combination, decomposition, single replacement, and double replacement. So I hope you can answer this at home. Practice more. You review books to have more examples, to practice more on balancing, writing equation, predicting products, classifying chemical reactions. So